Today we want to look at some more equation stuff. This is for when our overall plan of doing inverse operations in reverse order is not going to work, primarily because the variable appears more than once. So we're going to try to cover some situations where inverse operations in reverse order is not going to help us. So what if, oh, I'm not sure I'm allowed to say what if, because Marvel owns that now. Or that's a Marvel thing and Disney owns Marvel. So Disney's going to come after me. So if on Tuesday I'm not here and like it's Professor Mickey Mouse, you'll know why. So what if inverse operations in reverse order isn't going to work? So one of the ways that inverse operations in reverse order isn't going to work is that the variable appears more than once. In this case, the variable is appearing more than once in a quadratic, so that's a little bit cheating on my part. We could write this so that the variable appears only once. Maybe we should, but for right now, we're just going to take this as an example. So one of the reasons that will cause inverse operations in reverse order to not work is that the variable appears more than once. So we can't just track a list of operations on the variable. So let's take a look at this equation. We've got 2 cosine squared x plus cosine x minus 1 equals 0. This is an equation that comes up all the time, like twice a year for me. I don't know if it comes up twice a year for everybody else, but it comes up twice a year for me. And I choose to believe that this must be happening all the time if it's happening to me so often. What we want to do is notice that there's, first of all, notice that there's more than one instance of the variable. So we're not going to be able to do inverse operations in reverse order. What we want to look past is that the cosine is sitting inside of some other function. If we look carefully at this equation, we see cosine squared and then cosine and then a constant. So this is a quadratic in cosine. So we should see the quadratic 2, I don't want to use x, I need something else. Let's say 2w squared plus 1w minus 1 equals 0. So notice that this equation is quadratic in cosine. I want to read 2 cosine squared plus cosine minus 1. If I replace the cosine with just w, then I'm looking at a quadratic equation, but with cosine instead of just w. So what we can do is make a substitution. I can trade my cosine for w. We're going to substitute w equals cosine x. And that'll turn our equation into 2w squared plus w minus 1 equals 0. This is number 3 of the 3 best tricks of mathematics. Number 1, add 0. Number 2, multiply by 1. Number 3, trade your variables for something easier. And that's what we're doing here. We're trading our cosine x for just w. Now that we've broken this down to a quadratic equation, we can solve that by whatever means we deem necessary. And in this case, unsurprisingly, it's factorable because I don't pick problems at random. And moreover, it's kind of easily factorable because there's only one way to get 2w squared, that's 2w times w. And there's only one way to get a -1, that's a 1 times a 1. I just got to figure out which one is going to be negative. I want a positive w, so I'm going to need a plus 2w and a minus w. So we substitute w equals cosine x. And in this case, our quadratic happened to be factorable. And so we get two solutions for w. We get that w is equal to 1/2, and w is equal to -1. But so this is two solutions for w, but what about x? We weren't trying to solve for w, we were trying to solve for x. Now we can take our problem back to cosine. Earlier we got here by stating that w is equal to the cosine of x. So now I'll just replace my w's with the original cosine x. So we go back to x. Only do this in math. Don't do this in like life. Cosine x is 1/2, and cosine of x is equal to -1. And now we just have these two trig equations that we need to solve. For cosine x equals 1/2, let's see, x, I didn't specify whether we're using radians or degrees. So let's just use radians because it's more fun, even though it might keep us up at night. So with cosine and 1/2, we have a reference angle of 60 degrees. So first our reference angle. So 60 degrees. And cosine is positive, so we want to put it in quadrant 1 and quadrant 4. Cosine is positive where x is positive, and x is positive in quadrant 1 and quadrant 4. So pi/3 in quadrant 1 and quadrant 4. Oh, apparently I'm back to Roman numerals for quadrants again. We want to make sure that we get all the solutions. I didn't specify that we only need to go around once. So I'm going to put pi/3 in quadrant 1. And that's just pi/3. And the period is 2 pi, so plus n times 2 pi. I don't know why I said it backwards. It's 2 pi times n is how I normally write it. I also got to put pi/3 in quadrant 4. Since I'm writing all the solutions, an easy way to do it would just be to say negative pi/3 plus 2 pi n. If we don't like the negative pi/3, we could just put pi/3 in quadrant 4 and just do 6 pi/3 minus pi/3 and say 5 pi/3. So another option would be to say, or 5 pi/3 plus 2 pi n. The cosine and the 1/2 gave us the reference angle of pi/3. Cosine and positive gave us quadrant 1 and quadrant 4. And then the third step is to add integer multiples of the period. For cosine x equals -1, if we think about our unit circle, we want the x coordinate. We want to think about the angle where the x coordinate is -1. So we know that cosine starts off at 1, drops down to 0, and then continues to drop down to -1, and then goes back up to 0, and then back up to 1. So cosine of 180, or cosine of pi, is equal to -1. So the cosine x equals -1 gives us the solution x equals pi. And since we want all the solutions, we add the period times an integer. So 1 pi, 3 pi, 5 pi, and so on. If we think in terms of, if we don't like the unit circle, we can remember that the cosine we know that cosine starts off at the top and then drops down to the bottom halfway through the period. And so that happens at pi. Five pi over 3 is another name for -pi/3. I needed to put a pi/3 reference angle in the 4th quadrant. So I've got these 3 solutions here. So I needed to put a pi/3 reference angle in the 4th quadrant. So I'd have pi/3 in the 1st quadrant. And so I needed to put a pi/3 in the 4th quadrant. And so one way we can do that is we could take 2 pi minus pi/3. 2 pi is 6 pi over 3 minus pi/3 for 5 pi/3. So that's the 5. That's where the 5 pi came from. So we get an infinite number of solutions, but here are our 3 basic solutions. Pi/3 and all the coterminal angles with pi/3, -pi/3 and all those coterminal angles, and then also pi and all those coterminal angles. Any questions?
One quick clarifying question.
Yeah.
How did you, so -1 on the I guess the pie chart is pi.
-1
correct?
on the unit circle, yes.
On the unit circle, my bad, yeah.
Yeah, so the unit circle has theta equals 0 on the positive x-axis. And so going around, theta is equal to pi at -1, 0.
Oh, so it's just -1 of pi.
No, it's just that we're just looking for the x coordinate. Because remember, any point on the unit circle, the coordinates are cosine theta and sine theta. So if I'm saying cosine of theta is equal to -1, I'm looking for points on the unit circle that have an x coordinate of -1.
Oh, okay. I get you, because it has to do with where it is and which coordinate it is. And
yeah. So we're looking, when I say cosine x equals -1, I'm looking for where, x is a bad choice there. Cosine of theta equals -1. I'm looking for the theta that has on the unit circle that has an x coordinate of -1.
That's an x coordinate of -1. Okay, I was thinking you were talking about like on a graph. I was like thinking, where does the -1 come in?
Right.
That makes sense though, now that you just explained it. Thank you.
Let's put a -1 down here. Any questions? How's everybody okay? I like to do small changes to things. Let's do a small change. Because this is fun. So let's look at for a second example. I'm going to keep the quadratic. I'm just going to trade out I'm going to keep the quadratic. I'm just going to replace our cosine with sine. when we're doing a selection of problems, when I'm trying to build a selection of problems, I try to not have the problems just live in all these little silos and be separate problems. I think the problems need to follow some kind of progression. Now, I haven't figured out the ideal form that progression should take, but the idea is that once we do a problem and get an understanding of that problem, I want to move on to, I want to change a small aspect so we can still rely on the stuff that we used in the previous problem and see what the new problem brings to the table. So I'm going to switch up just a little bit and go from cosine to sine. Structurally, everything else is the same. Is the middle, it was plus. Yeah, okay. So similar problem. We're gonna view this as quadratic, and we're gonna make the substitution W equals sine x. This is going to change some things at the end of the problem, not so much at the beginning of the problem. I'm still going to read this quadratic as 2w squared plus w minus 1 equals 0. That part isn't changing. So it's still going to factor out the same way. 2w and w and 1 and negative 1. Plus 2w minus w is plus w. Okay. And so we still get w equals 1/2 and w equals negative 1. That part didn't change. We're just looking at a quadratic in sine, not quadratic in cosine. But now when we substitute back the w's, we have sine x equals 1/2. And sine of x is equal to negative 1. Now things have changed. Now for sine of x equals 1/2, my reference angle is going to be 30 degrees. So 30 degrees. And we're going to put it in the quadrants where sine is positive. So this is going to go in quadrants 1 and 2. Oh, now I'm back to these numbers. So I'm going to put pi over 6 in quadrant 1. And that's just pi over 6. And I'm going to make sure I get all the solutions. So plus the period times some integer. I'm going to have to put pi over 6 in quadrant 2, and that's 150 degrees, or 5 pi over 6. And I'm going to have to get everything coterminal with the 5 pi over 6. So in this case, I want to put a pi over 6 radian angle in quadrant 1 and quadrant 2. So I need pi over 6 here and pi over 6 here.
So the way that you get these values is you look at where it's sine, positive sign or negative, where sine would be positive or negative on the unit table or unit circle, my bad, correct?
Yes, that's one way of thinking about it. We could think about if we put things on the unit circle. Remember that every point on the unit circle, the coordinates are cosine theta and sine theta. So I'm looking for where the y coordinate is positive on the unit circle. That happens in quadrant 1 and quadrant 2.
Okay, and then where do you, like, how do you decide? Because since both of those are positive and you were using the fact that sine x equals 1/2, that would equal that sine is equal to a positive. So how do you decide from which quadrant? Because it's sine is positive in quadrant 1 and quadrant 2.
Right, so we got to write down both. That's why I got pi over 6 plus 2 pi n. That's my quadrant 1. And I also have to get 5 pi over 6 plus 2 pi n. That's my quadrant 2.
And you're going to do the same thing for sine of x is equal to a negative number. So it would be 2 other quadrants.
Yeah, if I had sine of x equals negative 1/2, then I would be using quadrant 3 and quadrant 4. Here's my quadrant 1, and here's the stuff from quadrant 2.
Got it. Okay, perfect.
If
Thank
it
you.
was sine x equals -1/2, then I would still have pi over 6, but I would put it in quadrant 3 and quadrant 4.
And okay, and then that's what you're gonna do with sine of x is equal to -1. The second part
Yes.
on the right. Okay.
So the trick here is that when we have sine of x equals -1, this one's going to land on one of the quadrants, because now we're looking at this point, 0, -1. Because on the unit circle, we're looking for the angle that has a y coordinate of -1. And so this happens at 3 pi over 2, or 270. So this part of the equation is going to give us an x of 3 pi over 2, and then everything coterminal with 3 pi over 2. So in this case, we're not doing a quadrant thing so much, because the -1 puts us in between quadrant 3 and quadrant 4. So still below the x-axis, so the y coordinates are still negative.
Okay.
But because it's a sine of x equals -1, that's going to be just that one point. It's going to be in between quadrants. So if we think about the graph of sine, we're looking for where sine is -1, and that only happens at this one point at 3 pi over 2.
Okay, because it only happens
It only
in the
happens
fourth
once.
quadrant.
Yeah, it happens when it's crossing over between quadrant 3 and quadrant 4. If I had anything less than -1 that's still negative, then I'm going to be looking at 2 points. Because I have quadrant 3 negative and quadrant 4 negative. I'd have 2 points. But since it's -1, that puts us right at this lowest point.
Okay, gotcha. Thank you.
Any questions?
Can you summarize one more time why we add the integer multiple of the period and what goes wrong if we don't do that?
So nothing goes wrong if we don't do that. But remember what the graph of sine looks like. So remember that the graph of sine is periodic. If we can list pi over 6 and 5 pi over 6. Those will be those first two solutions. I put the pi over 6 in quadrant 1 and also in quadrant 2. So this is where we have, say, pi over 6, and here's our 5 pi over 6. But those aren't the only two solutions to sine of x equals 1/2. If I draw this line, the horizontal line through 1/2, we can see there are going to be in many more solutions. So what we're observing when we write plus 2 pi times n is we're acknowledging that there are an infinite number of solutions. And in this case, it's because the sine is a periodic function. We see the same thing from 2 pi to 4 pi that we saw from 0 to 2 pi. And so what we want to do, make sure we do, is add a 2 pi to each of these. And it says 2 pi times n because after the first time we add 2 pi, we're going to have 2 more solutions. And we're going to have to add 2 copies of 2 pi. So adding 2 pi is going around the circle once. So we want to get pi over 6, but we want pi over 6 plus 2 pi, because that's the same location. Now, if I asked you to solve this equation and you just gave me pi over 6, 5 pi over 6, and 3 pi over 2, I would be super happy with that, because it didn't specify give me all the solutions. So if you give me all these 3 solutions, it's just one small step to say, to include there are more solutions. So nothing bad happens. We still get at our important, the core 3 solutions. But then we have to remember that these trig functions, sinusoidal functions, are periodic functions. So they're an infinite number of copies of the sine. So we've got an infinite number of solutions. It's not just pi over 6, it's everything coterminal with pi over 6. It's not just 5 pi over 6, it's everything coterminal with 5 pi over 6. And that'll happen at integer multiples of the period. So I told you these trig equations were fun. This is fun, right? I don't know.
Yeah, I got one quick question. So but I think I missed this part because I don't think I was understanding before, but I think it just clicked. So to be clear, when you're on the unit circle, when you say coterminal, say you only go halfway into the first terminal, you only count that terminal, right? But then when you did the second one where it went all the way into the fourth terminal, it's everything coterminal with how far you just went, correct?
No, coterminal
Fourth quadrant,
means,
my bad, not terminal.
coterminal means ending at the same. So all these solutions, pi over 6 plus 2 pi n, that's all the quadrant 1 stuff. These are all coterminal, which means so. So here's the angle pi over 6, but that's not the only angle that ends there. That's pi over 6 in quadrant 1, but that's not the only angle that ends there. I could end at that. I could start off at x, and I could go all the way around. So past the pi over 6, go all the way around. And that's pi over 6 plus 2 pi, one full circle. Because if I start off at pi over 6 and go around once, so pi over 6 plus 2 pi. And then we can do that as many times as we want. I can do pi over 6 plus 2 times around the circle. So there's pi over 6.
Extra.
And if we go all the way around the circle, that's pi over 6 plus 2 pi. And then if I go all the way around the circle again, that'll be pi over 6 plus 4 pi. Now we've gone so far, I didn't even draw the terminal side long enough. And we just want to make sure that we're getting all of the solutions.
Okay. And for x equals 3 pi over 2 plus 2 pi n, that would go, since could you draw that out how you drew
Sure.
The first one?
Yeah. So we're looking on the unit circle. We're looking on the unit circle where the y coordinate is -1, and that happens at 3 pi over 2. So if we go around, there's theta is equal to 3 pi over 2.
Okay. And it's in the fourth quadrant, correct? Or is it just
That's in between quadrants. 3 pi over 2 is in between the third and the fourth quadrants. That's why we only got one. That's why we only got one solution. Instead of saying in quadrant 3 and quadrant 4, the 3 pi over 2 is in between quadrants. We're on the boundary between the two.
Oh, okay. It would be there if I looked at the unit circle.
Right.
Correct.
So that would be like if you're standing exactly on the border in that hotel that's on the California-Nevada border, you can think of yourself as being, if you were infinitely thin, you could say, I'm neither in California nor am I in Nevada. That's what's happening when you're here at 3 pi over 2.
Oh, okay, gotcha. And then so, which you don't, so it's okay, because I remember I was thinking, so then that's why you put it to 2 pi n. 2 pi n is the constant thing, right?
The 2 pi n is integer multiples of pi, because we can go all the way around the circle. I can go 3 pi over 2, and then I can go all the way around the circle again. And we're at the same spot. Or we can go from 3 pi over 2, we can go all the way around the circle a second time. And we're at the same spot. Every time I add another 2 pi, that's just adding another full circle, and we're still talking about the same angle. So if we did the sine of 3 pi over 2, -1. If I do the sine of 3 pi over 2, and this time add 2 pi, one full circle, we get -1. If I add another full circle, that'll take us to 4 pi, -1. Because all these angles that I'm inputting are at the same place. I can go backwards too. Oops, I used the wrong negative. I can go backwards too. Because all these angles, 3 pi over 2 plus 2 pi times some integer, those are all the same place. So the angles we say are coterminal, and so they'll have the same sign. Any questions? It only seems like it's a lot to remember because it's a lot to remember, and you have to remember all of it all the time in perfect detail. Any other questions? So what we did in these problems is just add a little bit more stuff before we get to the basic maneuver of the trig equation. The basic maneuver of the trig equation is to find the reference angle and put the reference angle in the appropriate quadrants. And then add the multiples of the period. So one of the reasons that we want to make sure that we include the plus 2 pi n to add, say, all the solutions is that we might have another variation. So let's suppose that I had this equation. Let's suppose I had 2 times the sine squared of not just x, but what if I had 3x plus the sine of 3x minus 1 is equal to 0. Make a small change. Instead of sine of x, now I've got the sine of 3x. So now instead of having a period of 2 pi, I've got sine of 3x, and so that has a period of 2 pi divided by 3. So instead of a period of 360 degrees, I got a period of 120 degrees. Our initial approach is the same. We recognize this as being quadratic in sine of 3x, and so we'll substitute w equals sine of 3x. 2w squared plus w minus 1. Saved it, kind of. So we still get the same quadratic, and so we still get the same solutions. But now when we unsubstitute our w's, it's not the sine of x that we're looking for, it's the sine of 3x. So if we think about the order of operations and what happens to get x to 1/2 in the sine of 3x equals 1/2, first we multiply by 3, second we do the sine. So the first thing that we're going to have to deal with is the sine inverse, which means reference angle in the appropriate quadrants. So our reference angle for 3x this time. So our 3x reference angle is still going to be pi over 6. And I still want to put the pi over 6 reference angle in quadrants 1 and quadrants 2. So instead of saying x is equal to pi over 6 plus 2 pi times n, I'm going to say 3x is pi over 6 plus 2 pi n. This is all my quadrant ones, or all my quadrant 1 angles. But I also have to list the quadrant 2 angles. And I'm just dealing with the sine inverse right now. I'm not worried about dividing by 3 yet. So 3x equals 5 pi over 6. That's pi over 6 in quadrant 2. And I have to add multiples of 2 pi because that's the period. I also have over here sine of 3x is equal to -1. So 3x is equal to 3 pi over 2 plus the circles for the coterminal stuff. That's to make sure that we get all of the solutions. But at this point, we've just solved for 3x, and we weren't asked to solve for 3x, we were asked to solve for x. Technically, we weren't asked to do anything in this problem. I can say, here's an equation, like, oh, great, you didn't tell us to do anything with it, so, and then log off real quick before I ask you, or sign homework or something. But we need to solve for x, and that just means dividing everything by 3. So for my quadrant 1 stuff, I get x by itself will be pi over 6 divided by 3 is going to be 18 plus 2 pi over 3 times n. My 5 pi over 6 will be 5 pi over 18 plus 2 pi over 3 times n. And here, 3 pi divided by over 2 divided by 3 will be pi over 2 plus 2 pi over 3 times n. So here are our infinitely many solutions now. Any questions? Now, if we were restricted, if for some reason the problem said solve this equation for x between 0 and 2 pi, we can see we're going to get some more solutions than just the pi over 18, 5 pi over 18, and pi over 2. There are going to be some other angles in between. Or yeah, there are going to be some other angles between 0 and 2 pi. Any questions? Sometimes it helps to think of the problem in degrees. So right now, I decided to do all of today in radians. But let's think in degrees, what's going on. So let's pick it up from here, where 3x is equal to 30 degrees. Instead of 2 pi, I'll use 360 degrees times n. And then I got 3x is equal to 150 degrees plus 360 degrees times n. And this solution over here says 3x is equal to 270 degrees plus 360 degrees times n. When we go through and divide by 3, x will be, this 30 degrees divided by 3 is 10 plus 120 times n. Notice that 10 degrees is pi over 18. Pi is 180 degrees divided by 18 is 10, so it's matching so far. 2 pi over 3 we know corresponds to a 120 degree angle, and there it is, 120. And so x equal to, if I divide the 150 by 3, I get 50 degrees plus 120 degrees times n. And 270 divided by 3 is 90 degrees plus 120 n. And I got the pi over 2 in radians, and that's 90 degrees in degrees. If we wanted to start making a list of the solutions, I have 10 degrees, 50 degrees, 90 degrees. 10 plus 120 is 130. 50 plus 120 is 170. 90 plus 120 is 210. And we can also go backwards. 90 minus 120 is negative 30. So there are an infinite number of places where this equation is equal to 0. It happens when 3x is pi over 6 in quadrants 1 and quadrants 2, and when 3x is equal to 3 pi over 2 in between quadrants 3 and 4. Any questions? Cool. So earlier I had mentioned that if we have a quadratic, we can rewrite a quadratic so that the variable only appears once, because I can always rewrite ax squared plus bx plus c, where the variable appears more than once. It has a vertex form, a times x minus h squared plus k. And so here the variable appears only once. And all we have to do is complete the square. So if we have 2x squared plus x minus 1, we're really just looking for the vertex of this parabola. Let me grab, oops, I didn't have Desmos open. Let me open a Desmos. Such a good graphing calculator. So if we look at y equals 2x squared plus x minus 1, we can see the vertex down here at negative 1/4 and negative 1.125. So that's, I was just doing decimals. Negative 1/4. So x minus a negative 0.25 minus 1.125. Now, if we wanted to solve the equation, we could just add 1.125, divide by 2, take the square root, which will lead us to a plus and a minus, and then subtract the 0.25. So now we can, if we set this equal to 0, we can do the inverse operations in reverse order. We would just add 1.125, so 2 times x plus 0.25 squared is equal to 1.125, divided by 2, x plus 0.25 squared is equal to 1.125 is 9/8 divided by 2 is 9/16. Take the square roots. Oops, I forgot to stop sharing. Take the square root, which is where the plus and minus shows up. And then subtract a fourth from both sides. Negative a fourth plus 3/4 is a half. And negative 1/4 minus 3/4 is the -1. Those are the two values that we got before from factoring. At this point, we would recognize, oh, heck, this was factorable. But at this point, we wouldn't want to go back and factor it. Any questions? Now, this was only one example where I focused on taking a quadratic and putting in one instance of the a trig function. I just replaced the x with sine of theta, or I replaced w with sine of theta, or sine of 3 theta. If I had started doing other combinations of things, if I said 2 sine of 3 theta plus sine of 5 theta, now all of a sudden we got a big mess, because we have two different periods working in our sines. And so that's gonna mess everything up as far as solving that by hand. Time to break out the machine. If I've got a combination of, let's say, sine squared of 3x plus 5x, now I've got a combination of a polynomial function and a trig function. Time to break out the machine. So this, where we substituted the w equals sine of x, or even sine of 3x, that was because the problems that I presented today were very contrived to do a very specific thing, the thing that I wanted. If I had changed the arguments, made it look very similar, all of a sudden we've got a problem. I can't resolve this. One of them is a 3x and the other one's a 5x. I don't have the same period. I can't say w equals, and what am I going to say w equals? I'm going to have two different things. If I have 2 sine squared of 3x plus just a 3x, no trig function, then it's the problem is this sine and this 3x. I've got trig function combined with polynomial function. Pen and paper are now off the table, because now I'm giving you problems and that you don't have the tools for, and so you flip the table. That's why the pen and the paper are off the table. There are some things that we can do. If I do this combination, 2 sine squared of 3x plus cosine of 3x. The arguments match. They're both 3x, but I got a sine squared and a cosine. So this part, the 3x, that's good. But the sine squared and the cosine, the sine here and the cosine, so let me tell you what to do in this situation. Now, we can only do this because we have a sine of 3x and a cosine of 3x. And once I tell you what to do in this exact problem, it will make all of trigonometry instantly snap into place. Like I plugged you into the matrix and just downloaded trigonometry into your brain through that big giant hookup. They don't have USB in the future, I guess. But once I explain what to do in this problem, it will make trigonometry Just super easy, and you'll understand it instantly and forever. And all of the rest of your math classes will just be perfectly easy. And you're just going to get constant A's. As long as I tell you right now, if I wait any longer, then the magic is not going to work. And you're just going to have to struggle through your math classes like always. So here's what to do. Because of the sine of 3x and the cosine of 3x, to make math easy for you for the rest of the life, all you have to do is, oh, darn, look at the time. Shoot, I guess we'll have to wait, and math will forever be a struggle. That's going to do it for today. That's going to do it for this week. I will see y'all on Tuesday. Everybody have a good weekend. Figure out what to do in this scenario, and let me know on Tuesday. That's it for this week. I'll see y'all on Tuesday. Everybody have a good weekend, and thanks for playing.
Thank you.